Let's take a look at Unit 4. Unit 4 has 6 modules, as you can see, Module 16 through Module 21. And we're going to take a look at Module 16 today, which is essentially just explaining what sensation is in comparison to what perception is. Let's get into the kind of basics of the vocab. The goal is to take a look at the vocab from a standpoint of getting ready for your vocab quiz and kind of picking apart the vocabulary itself, but also taking a look at the concepts that you need to understand for your test as well. So from conceptual understanding, the word sensation really, to sense means to detect, to encode. Essentially, it's almost the same thing as encoding. Sensation and perception refer to the way in which we create a reality based on the physical properties that we experience in the world. And to simplify that and really kind of make it more understandable, sensation is in reference to the 5 senses that we have, which is the literal way in which the human brain experiences the world. What that information is encoded and transferred, what's called transduction, into in the various parts of the brain, and what your brain does with that, how it makes sense of it, in other words, that's referred to as perception. So sensation is the process by which we actually encode and receive energy from the world around us. So for instance, the job of the ocular system, the eyeballs, is to detect light waves. The job of the auditory system is to detect sound waves. And what your brain does with that information is to create an experience of the world. So sounds aren't just pitches and frequencies, they are melodies, they are tunes, they are words, they are sentences, they are potential predators, they are alarming or alerting or soothing. So the way that our brain makes sense of the information that is being brought to it by the 5 senses is considered perception. That's the organizing, that's the interpreting, that's the recognition, and that's the creation of meaning. And an easy way to think of the difference between the two is sensation is going to happen at the sensory level, obviously. And that's going to be the senses that you know of. That's going to be the eyes, the ears, the skin cells, the olfactory system in your nose, the ability to taste, the taste buds in your tongue. But the perception is what's happening in the cortex of the brain. It's not the senses themselves. It's the surface of the brain that's processing the information. In other words, the eyeballs are responsible for sensation, but the visual cortex is responsible for perception. And the cochlea of the ear, as in the tympanic membrane, which is the eardrum, are responsible for detecting sound, but the auditory cortex of the brain is responsible for perception of sound. So the actual sensory parts of your awareness are different than what the brain does with that information, which is perception. So again, your nose, eyes, or other sensory organs bring information, and then your brain makes sense of that, basically creates a perception of it, an understanding of it. Is this sight something that we need to be aware of? Is it something that we've seen before? Is it something that's dangerous? Is it visually appealing to the eye? Is it something that's harsh? The brain makes sense of data and essentially creates our perception of reality. And our perception of reality is nothing more than a collection of information that the cortex of the brain has identified based on physical data from the world around you. And you can only perceive what you can sense. Well, in theory, you can typically see what you perceive what you sense, but you can only sense what's immediately in the detectable range, what's called the threshold of your eye. So for instance, there are light waves that are all over the world that we can't detect because they're out of our range for sight. Those light waves will never travel far enough to get to our retinas, and therefore we can't see them. That's what happens when we can't see things. You close your eyes or you're out of the distance range for those actual light waves, and therefore obviously the auditory or the visual cortex, excuse me, can never see them. So think about, from a literal standpoint, the process of taking in odors. So scent molecules from things like this rose are the molecules themselves are the odors, and they're going to enter into the nose. Then the olfactory bulb is going to detect them as a scent, and then it's going to be brought to the chemical center of the brain, and it's going to be perceived as either a positive smell or a negative smell, meaning a pleasant smell or an offensive smell. And so the actual detection of the molecules themselves is a type of sensation. This is a concept that you really have to pay close attention to, because not only will you get several test questions on this in the future, this is one of those combinations of vocab pairs that people tend to get confused. So pay close attention to bottom-up processing versus top-down processing. They are metaphorical terms of how your brain processes data. That's really the best way to look at it, how your brain processes data. So bottom-up processing is a raw sensation in its most literal form. It is how your brain experiences something without any expectation or without any preconceived notions. So you walk down the beach in bare feet and you step on a shell, and the shell is sharp and you feel pain. Well, your experience in that scenario is an example of bottom-up processing, because you didn't have an expectation of pain, you didn't have a psychological concept of pain. Basically, the level of pain that you are experiencing is just because of the actual experience from the sensory tissue in your skin in this case. So bottom-up processing seems complicated and confusing, but it is really just an actual level of sensory experience without any expectation, without any preconceived notions, without any prior process. And it's easier to understand bottom-up processing when you compare it to top-down processing. So top-down processing is what happens when you've experienced something previously before. So for instance, if instead of walking on the beach with bare feet and stepping on a sharp shell, let's say that you're going to the doctor to get a vaccination, to get a shot, and you have had a shot before, and so you know that it's going to be painful, and you use this process of top-down processing in order to anticipate the pain that you might feel when you get the shot. So your level of pain or your experience in that scenario is an example of top-down processing, because it's not just the pain that you feel from the actual prick of the needle, it's pain that you anticipate, pain that you create in your mind, pain that you think or that you build up emotionally and psychologically. So in other words, it's an expectation, and expectations can influence our experience. Right? So let's think of it in terms of something other than pain. What if you taste a food for the first time ever? Well, bottom-up processing is you have no prior expectation because you don't know what to expect. So if you eat something for the first time ever, like say you eat a raw oyster for the first time ever, you're going to be tasting that, and your experience of it should be bottom-up processing, because all you should experience is the fact of the actual taste of the oyster itself. But in reality, you may be experiencing top-down processing, because top-down processing is something that your brain's expectation and your brain's, let's say, your brain's prior experience or your brain's expectation is going to change the way that you actually experience, in this case, the taste. So if you are off-put by the texture of the oyster or the smell of the oyster, or you've created this idea in your mind that it's going to be disgusting, then you're probably not going to enjoy it. And it's not because of the taste, it's because of the top-down processing. It's because of the expectation that your brain has created. So essentially, top-down processing is your brain's anticipation and expectation and the way that you experience something based on that. Bottom-up processing is experiencing something without any expectation, right? And so that's top-down processing versus bottom-up processing. And just to keep them separated, you can think of any example that you want using any of the five senses that you want. But bottom-up processing is almost as if your brain is experiencing something at face value for exactly what it is. Top-down processing is your brain has created an anticipation or an expectation, and that's definitely going to influence the way that you experience it. So that can be good or it can be bad. If we build something up in our mind, it can help us to enjoy the experience more. Or if we build something up in our mind, it can be disappointing. So top-down processing is more than just the actual sensory experience. It's all of the mental processes involved in the experience itself. And so that's usually prior experience is some kind of a buzz phrase that you'll see in an example of top-down processing, but it's anything that you can do mentally, cognitively, psychologically, or emotionally that will either enhance or will downgrade the experience of something. So based on experience, based on expectation, based on emotional status, that's anything cognitively or psychologically that's going to either make a sensory experience more extreme or it's going to enhance it. And that's top-down processing. So when we get into other sensory tricks and sensory things, we have to be reminded of a previous concept that we learned about, which is this idea of dual processing. The fact that your brain is trying to do two different processes at any given moment. And one of those is going to be the subconscious things of keeping you alive, those brainstem things. But the second thing is your conscious awareness. And your conscious awareness of how you're experiencing the world or going through your day or what you're thinking about or what you're feeling or homeostasis or all of these things, those are all parallel. And what I mean by parallel is the idea that you can really only focus on one thing at a time. So that's selective attention. Parallel processing is explained by selective attention. The idea that 5 of your senses are constantly competing for your brain's awareness. And so the one that is the loudest, which is probably problematic because you think of a sound, but the one that is the most prevalent, we'll say, usually gets the attention of your awareness, of your frontal cortex. So if you're outside on a cold day and the temperature is freezing, then your uncomfortable feeling or your sense of touch in the sensory cortex might get most of your attention. If there's a really loud noise happening, say during a fire drill, then your auditory cortex or your sense of hearing might get the focus of your brain's attention. It really just depends on which of those parallel processes are being stimulated or activated at any given time. So selective attention is the tendency to focus on one of the physical stimuli, we call those sensations, among other things that are happening. And so you listen to a sound over pay attention to a sound over a sight. You pay attention to the temperature or the feeling of pain over sight or sound. But even inside of all of the sounds that you hear and all of the sights that you hear and all of the smells that you're inundated with, your brain will pay attention to one over the other, right? So you have to pay attention to what stimulates the brain the most. So if we're talking about a room full of sights, there's a lot of colorful things happening in a room or a lot of movement, we'll say. What is it that your brain pays attention to or grabs a hold of? Here's a good FRQ term that I've seen, and it's a vocab word that's known as the cocktail party effect. The cocktail party effect is a very specific vocab term right? It is a type of selective attention, but it is not a synonym for selective attention, because selective attention can be any of your senses, and the cocktail party only affects sound. It only affects the sense of hearing. And the cocktail party effect is that form of selective attention where you hear your name. And that happens when your friends are across the room and they're talking and you're not really particularly paying attention to what they're saying because you're engaged in your own conversation, but you hear your name. And your ability to hear your name, even when you're not paying attention, your brain's ability to detect that, that's a form of selective attention that's called the cocktail party effect. And that's the most common form of selective attention. That's usually what happens when your parents complain about you having selective attention, actually, or your teachers. They're usually referring to the cocktail party effect because it's the most common form of selective attention. And so you're at a crowded party with lots of friends, everyone is talking and it is loud, or you think about something like you're at a basketball game or you're at a pep rally. You're focusing your attention on the conversation that you're having, but then you hear your name from across the room. So that's the cocktail party effect. It's defined as your ability to pay attention or notice or detect one sound, particularly your name, in a loud din of other sounds. So other examples of selective attention and why it can be problematic is the obvious one of divided attention. So a selective attention is the idea that we really can't pay attention to multiple things at one time. The data is pretty clear on that. We think that we are simultaneously talking on the phone while we're driving, but in reality is that when we're focusing on what we want to say, that we're not paying attention to the road. So as long as nothing is unchanged, or as long as nothing is changed in the picture of the lanes around us, then we tend to be okay. So one of two things is true: we're either paying attention to our conversation and not paying attention to the road, or we're paying attention to the road and we're mindlessly having a conversation. So either of those is possible, but you cannot focus on multiple stimuli at one time. It is cognitively and neurologically impossible to do. So look at research, just some scientific empirical data that's been shown to or studied to show the problems with distracted driving and selective attention while we're driving. fMRI scans show 37% decrease in brain activity that are vital to driving when a driver is listening to a conversation. And that's kind of troubling because that's just listening to a conversation. It doesn't actually say engaged in a conversation. In Australia, in 2005 and 2007, there was a University of Sydney study that was done that found that cell phone users are 4 times more likely at risk for a car crash than non-cell phone users, which again, that's a significantly higher number. And even when you account for confounding variables, that's statistically significant at 4 times higher. And then another example in NFC study that was done in 2010, the National Safety Council found that 28% of traffic accidents occur when drivers are chatting on cell phones or texting, which again, 28%, you think that's just over a quarter, but that's a very avoidable distraction. So these are just examples of selective attention and basically science that shows, or studies at least, that show that you can't really pay attention to conversations and drive at the same time. So basically the idea there is driving on a road while talking on the phone is one thing, but if someone pulls out in front of you, or if someone slams on their brakes, or if there is a change in the stimuli in the environment around you, your reaction time may not be what it should be. So again, it's not the phone itself, and this is important because of the studies that have been done with hands-free sets. So what happens if you have Apple CarPlay, or what happens if you have some kind of Bluetooth headset, or what happens if you're, not holding the phone or looking at the phone. It's not just the fact that your eyes are off the road, it's the fact that your attention is off the road. And that's important to understand. It's not just the fact that you're not looking at the road, which obviously is dangerous. Texting and driving is much more dangerous than talking and driving, obviously. But even if you're looking at the road, it's that your attention is divided. So using a cell phone, even with a hands-free set, or even when they accounted for a hands-free set in this study, it didn't change the statistical likelihood. You're still 4 times more likely to get into a car accident than if you're not talking on the phone, which is an equal risk to driving drunk, which is kind of staggering to think about. Selective inattention. Selective inattention is obviously going to be the opposite of selective attention. So whatever we're paying attention to is selective attention. So those things that we are not paying attention to are the things that are selective inattention. So selective inattention is natural and unavoidable. It's easily cognitively explained, but the term selective inattention refers to the things that we miss even though they're clearly inside of our threshold. So for instance, what are the things that we don't see because we're not paying attention to them? What are the things that we don't hear because we're not paying attention to them? And so those aren't things like optical illusions. Those are things that we miss because we're focused on something else. So easily detectable. It's not like, well, I didn't see that car because it was around the corner. I didn't see that car even though it was clearly in my plain sight. So I've also seen the term selective inattention in an FRQ question, and basically what they want you to know in that scenario is that it's something that you could easily detect but weren't paying attention to. So I didn't notice the car driving up beside me and I changed lanes and ran into it. It's not that you couldn't see the car because your eyes were closed or that your eyes were diverted somewhere else. It's that you weren't paying attention. So that's the key word there if you ever get that on an FRQ. It's the things that you could easily detect that you don't notice because you're not paying attention to them. You're paying attention to something else. So an example of this, you've probably seen various versions of this, like on brain games and things like this, but I embedded this one that you can take a look at. Selective inattention. This is a commercial, I think from the UK.
This is an awareness test. How many passes does the team in white make? The answer is 13. But did you see the moonwalking bear?
Yeah, I like that it's a commercial for cyclists from the UK. But there's lots of versions like that. The example, they do a similar test on brain games with a guy in a gorilla suit, and I think they do one with a woman in a bikini. But the idea is simple. It's selective inattention. It's the things that are clearly in your visual field that you don't notice because you're not focused on them. You're focused on something else. And so these are the little details that we miss in when we're paying attention to something else. And that can happen in a crowded room, or it can happen when there's a lot of visual stimuli. It's for instance, the common example that I give a lot is, when you walk down the hallway at Gulf Breeze High School, it's very difficult to remember and notice what individual people are wearing. So it's a similar example from your book of the same video that you just saw. In this case, it's a woman with an umbrella. Change blindness is a similar vocab term, but change blindness is a very literal term. It is failing to notice subtle changes, or in some cases it's even really extreme changes because you're focusing on something else. There's an example where a sleight of hand magician changes his shirt while doing a card trick. Because you're focusing on the cards and focusing on his hands, you don't notice the change in his shirt. And the classic example was an experiment that was done with a construction crew passing by with a door. So you can see in the figure on the screen, figure A, figure B, and figure C. What happens in the experiment is a man walks up and asks a random stranger for directions, and while they are talking, two people pass by carrying a door or something like a piece of drywall that very, very quickly shields or blocks the view of the two, and they actually switch. So one of the guys that's holding the door switches place with the original guy who asked for directions, and the person who is giving directions doesn't notice that he's talking to an entirely different person. And they replicate this on Brain Games, which is a copyrighted clip that I can't show you here, but you can easily see the episode and see a version of that if you want. So essentially, while the man in the red sweater with the white hair is giving directions to a stranger, someone who looks similar enough to him but is wearing a totally different outfit emerges on the other side of the door holding the map, and the white-haired man doesn't even notice that it's an entirely different person. So in this experiment, or at least in this replication of the experiment, 67% of the people didn't notice that they were talking to an entirely different person after someone walked by and blocked their view for just a second. So transduction is an important vocab term also. This is the actual process that your brain's neurons go through in order to get sensory data to the cortex of the brain. So there's a couple of things that you need to know about transduction. One, just the fact that it's defined as the change in stimulus energies. So converting some physical aspect of the world around us into an impulse. So for instance, an example of transduction is the fact that there are not sights and colors and objects and shapes in the world around us. We obviously perceive those, but that's because it's all bent, refracted, and reflected light. So as light waves hit the retinas of our eyes, they are converted, which is the transduction, into neural impulses and brought to the visual cortex, which is in the occipital lobe on the back of our heads above the brainstem. So the transduction is the actual conversion of the light wave into a neural impulse. So that's one thing, is to just understand what the word means. But another thing is to understand that basically where in each of the sensory centers this transduction is actually occurring. So in other words, where is the transformation taking place? In the form of the eye system and the ocular system, transduction is taking place in the ocular nerve. So you have things like ganglion cells that convert light waves into neural impulses, because your brain doesn't use light waves, it doesn't use light vibrations, it understands impulses, neurotransmitters and molecules and stimulation of neurons. So what has to happen is your eyeball's job is to absorb the light waves. The ocular nerve brings that information through the thalamus to the visual cortex of the brain. And so that's the delivery portion. The transduction is in the cells that make up the retina, and the ocular nerve brings that newly transduced mental information or cognitive information to the actual brain. In the form of audition, which is hearing, transduction occurs in the cochlea. And the cochlea basically takes sound wave vibrations that are brought to it by the bones in the middle ear from the eardrum, and it converts them into neural pulses. And so when you get into the auditory system, you'll learn about the cochlea and what happens to bring those sound vibrations to the brain. Remember, all the stimulus energies that are around us are just waves. They're just vibrations. There are no sights. There are just light vibrations. There are no sounds. There are just, sound vibrations. There are no touches. That's just pressure vibrations. And so basically what our sensory receptors do are collect vibrations from the air around us and convert them so that our brain can make sense of them and create an experience of reality. Psychophysics, it's the study of the relationship between the physical characteristics of stimuli. Those are things like the ranges of megahertz for the light waves that we can actually detect, or pitches and sound frequencies that we can detect. So intensity, or pitch, or basically it's actual physical description of the characteristics of the vibrations in the world. So what is it about the smell, taste, and texture of buttery popcorn that produces the response in you? Well, it's essentially, in that case, it's bottom-up processing of a chemical response that your brain reacts to positively. It's a taste that pleases the pathways in the brain, reminding it, or at least telling it that it's a positive experience, that this is good food, this is food that is nutritious, which obviously is not the case, but it's chemically enhanced to trick your brain into thinking that it's nutritious. And basically there are chemical properties or physical properties that cause that experience to happen. And so how you study perception based on sensory characteristics is psychophysics. It's the actual mental physics, or let's put it this way, it's the actual physical characteristics of sensory data and how it affects your mind. So this is an important distinguishment to make for test purposes. The difference between the absolute threshold and the difference threshold, and people get confused, but it is a literal term, a literal distinguishment. Difference threshold is a comparative term, the difference between two stimuli. Absolute threshold is how much has to occur in order for you to actually sense it. So for instance, an example of an absolute threshold is at what decibel does a sound have to occur before we can actually hear it. That's the absolute threshold. The difference threshold is what is the detectable difference between two different sound decibels, right? So can we notice that one is an octave higher than the other one, or whatever unit we're using to measure it? Or when it comes to sight, the absolute threshold for sight is at what frequency does a light wave have to actually be at before we can see it. So there are things that above and below our threshold for sight. A difference threshold is a comparative term for two different stimuli that are not the same, obviously. So difference threshold is often referred to as the just noticeable difference. So if you see that in the question, that's difference threshold. So in other words, would you be able to detect with the naked ear that two sounds are different decibels? If you couldn't, it would not match that difference threshold. Whether or not you could hear the sounds at all is an absolute threshold. So speaking of sounds and sound detection, you would use tones. So basically, if you can detect the difference in a tone or two different tones and get it right 50% of the time on the test, then that it counts as stimulating the threshold for sound. So why are some people better at signal detection? Well, we have different thresholds. Some people have better hearing. Some people have better sight. Some people have maybe more sensitive skin to touch. And that has to do with our threshold. So if you have a higher threshold, that means that it takes more. So if your hearing is worse than your friend's hearing, that means they have a lower threshold for sound decibels than you do. So again, remember the absolute threshold is how much or minimum has to be present in order for you to detect something. So the examples they give, some teachers are more aware in detecting that you're texting in one class, but other teachers are not. They're not paying attention, maybe is the example, or in this case they're implying that they don't notice it, they don't see you. So it says, did you know that even when the parents of a newborn are exhausted from sleep deprivation, they can still hear the slightest whimper from their baby, even though the loud sounds of the trash truck or a screeching car outside may go completely unnoticed? And that's an example of selective attention. But basically, it's the difference in what you can hear compared to your friend, or what you can smell compared to your friend, or what you can see compared to your friend, or taste. That's a comparison of your thresholds. You might have more sensitive taste buds. Then the way to explain that in psychological terms would be that you have a lower threshold for taste than they do. So signal detection, again, that's the idea that your sensory receptors are capable of detecting data or stimuli. Let's call it stimuli. So how and when we can detect the presence of a stimulus, and it's the strength of the signal, right? Again, does it actually stimulate our minimum threshold for sound or for sight or taste, or is it below that or above that? So in other words, there are sounds that we can't hear because the decibels are beyond our threshold for sound. There's also sounds that we can't hear because they are below our threshold for sound. So the two conditions for signal detection, whether or not we can see, hear, taste, feel, smell something, whether or not the signal actually meets the threshold for what we can detect as humans, and our psychological state. Again, how alert are we? If we're really tired, we're probably not as alert, and we're not going to be able to detect signals at the same level. So you can see the light, but how can you tell when it gets brighter? Again, that's the just noticeable difference. That's difference thresholds. So if you've been in a crowd of families, like at a water park, and you yell "Dad" to get your father's attention, how does your dad know how to turn around? Well, that's because he recognizes your voice. It's that echoic top-down processing that your dad possesses, having known what your voice sounds like. How does a musician know when they are playing a little flat or sharp? Again, some people, and those of you that are musically inclined, you might have this ability. You might have a better difference threshold for sound pitches, which means that you have the ability to detect when you're off, when you're playing flat or singing flat, or when you're sharp, etc. That's because of your finely tuned ear, your difference threshold for sound. And how can you tell when just the slightest note of irritation is in your friend's voice? It's your ability to detect a difference in the sound. Weber's law is another principle that gets missed on tests, but it's really pretty simple. It's basically defined as a measure, a scientific measure of how much something has to change in order for you to detect the difference. So in other words, like, how much do you have to cut off of your hair every single day before your friend notices that you got a haircut? Or how much does a pitch of a sound have to increase? How many decibels does it have to increase before you notice that it is louder? How much does the font have to change in let's say, an entire page of text before you notice that it's a bigger or smaller font? So Weber's law is this idea that to be able to tell the difference between the degrees of stimulation, two stimuli must differ by a constant minimum percentage, right? So in other words, unless they increase by a detectable amount, you're not going to notice that they are different. So if I were to give you an entire bowl full of paper clips and ask you to notice when they get heavier. So if we put one more paper clip in the bowl, that hasn't increased, according to Weber's law, that hasn't increased by a significant enough percentage for you to notice the change. But if we put 1,000 paper clips in there, you might feel a change in the weight. And the same thing is true in your backpack. You might be carrying around 4 AP textbooks and it's super heavy. And so if you put, a computer printout in there, you're not going to notice the weight difference. But if you put one more textbook in there, you are going to notice the weight difference. So Weber's law is a way to quantify the percentage of how much something has to increase or decrease in order for you to actually detect that it has changed. So examples, 2 lights must differ in intensity by 8%. Otherwise, you won't notice that they have changed intensity at all. It has been calculated also that 2 objects must differ in weight by 2%. So again, in the example of the bowl where you're holding the paper clips, if we don't increase the weight total by 2%, you won't detect that the weight has changed at all. And in sounds, it's not much. 2 tones must differ in frequency by 0.3%, so 0.3%, in order for you to actually notice that the tone has changed. So Weber's law basically just creates a scientific way to quantify how much things have to change in order for you to notice that they are different. So we'll just kind of wrap it up there, but it says, how does Weber's law help explain the just noticeable difference? And again, that's the difference threshold. So the difference threshold is the minimum difference between 2 stimuli that are required for detection. And again, just like in that sound test, if you get them right 50% of the time on a test, which is, a failing grade to us, but if you get it right 50% of the time, that's enough to count that you got it right. And so basically, that's the scientific explanation of the percentage that something has to increase or decrease by in order for you to notice that they have changed. So we experience the difference threshold as a just noticeable difference. Weber's law tells us that the difference must vary by a constant percentage, not by a constant amount. So that the percentage, it's the percentage increase, not a measurable amount increase. And here's the example that's historically always been used. It's the idea that if you were to look at this passage that of the 23rd Psalm, and you start from the top and you read it as you would read any written text, by the time you get to the end of the passage, you wouldn't notice that the font has changed, because it does not increase by the detectable percentage unless you just start at the top and look at the bottom. So it is significantly bigger by the time you get to the bottom, but as you're reading the passage, the percentage of increase in the size of the font does not change enough for it to be detectable. So that's the first module of Unit 4. Then the other modules after this start getting into the various specific sensory systems, like the eye and the sight processes, the ear and the auditory processes, and then taste and even touch, things like the sensory cortex. So keep reading through the textbook and doing your study guide, and we'll get into the other modules as we go on.